All right, so I'm going to do kind of question 6 all together. So this is actually a bad picture of the Dirichlet function. This is a different type of it. And it's not the equation that I gave up here, so shame on me. So the way that this function would look is actually, if you were to look at it, it would look like you had a solid line when x is equal to 1. And it would also look like you had a solid line when x is equal to 0. The reason is that, just like you kind of can see down here, there's an infinite number of points that are going to be irrational. There's an infinite number of points that are going to be rational, and those points are going to be kind of infinitesimally close, right? So this is what this graph would kind of look like, almost like two vertical lines. But it's not two vertical lines, which is kind of part of like the interesting thing about this function. So in terms of the domain, well, x is a rational number, x is an irrational number. So if you took all the rational numbers and all the irrational numbers, oh, by the way, rational would be like, can be written as a ratio. This is fractions and decimals that end or repeat. This is fractions that do not end or repeat. So like pi and the square root of 2 and the cube root of 15. So if you put all the rationals and irrational numbers together, the domain is just going to be all real numbers. So you have a function that's defined for all real numbers. But here's the problem. So if you try to look at the continuity of this function, so if I just pick some number a, where I don't even know what a is, right? If I looked at what happens as you approach from the left and from the right, well, suppose this is like some rational number. So there's a rational number between any two irrational numbers and vice versa. There's an irrational number between two rational numbers. So if I get delta close to this rational number, there's going to be irrational numbers. So in terms of what this function would look like, right? So at the rational number, we'd be at 1, but at both those irrational numbers, we'd be at 0. So what ends up happening, right, thinking from like a delta epsilon perspective, as we get delta close to that rational number, that value of a, well, we can't. We're not just zooming in on that point right there because there are these two values, these two irrational values that are giving us f of x is equal to 0 in there. So what this means is that those limits are never equal to each other, right? Approaching from the left, I can either be at 0 or 1. Approaching from the right, I can either be at 0 or 1, whatever I actually want. So where is this function continuous? It's never continuous. So kind of, I think this is a pretty unique function, right? You have a function that's continuous that's defined everywhere. It's defined for all real numbers. However, it's never continuous, right? So you basically have some function that if you kind of like were to actually like be able to graph rational, irrational values, you'd be like 0, 1, 0, 1. So we kind of like bounce back and forth like this a whole bunch of times in terms of your function, your y values. So kind of weird, right? Kind of pushes the ideas of like what we think about a function being continuous, right? You can have something that's never, ever, ever continuous, but yet it's defined everywhere, which I think is pretty cool.